In this segment of the course, I'd like to briefly discuss the role of delay on the behavior of a dynamical system. And to make life simple, let's just consider a one-variable system. So we have a single variable x, and its time rate of change at time t is given by some function of x, but not x at time t, at x at some time earlier. And so we'll write this as f of t minus tau. So this is our prototypical one-dimensional delay dynamical system. Now, as written, this is actually an infinite dimensional system because we can perform a Taylor series expansion on the right-hand side, and so this would be equal to f of x of t minus tau df by dt at tau equals 0 plus tau squared over 2 d second f by dt squared at tau equals 0 plus dot dot dot. So there are actually an infinite number of time derivatives in this equation. And as we mentioned at the very first lecture, that this can be transformed into an infinite dimensional dynamical system. In disguise, this delay problem is actually an infinite dimensional dynamical system. That's part of the reason why they're so rich and so complicated. Now, another reason why we care about delay dynamical systems is that they actually have many important real-world applications. One of the first applications is in the early days of the Industrial Revolution when steam engines were developed. What you did is you stoked the boiler with coal and you would boil water. It would make a steam chamber that would then drive something that would turn a wheel and you would have an engine. Unfortunately, sometimes these steam engines had a propensity to blow up because you put too much coal in the boiler and it was boiling so hard that it was actually making the boiler fail. But if you put too much coal in the boiler, you couldn't go in and take the coal out. One had to develop control mechanisms so that when the steam pressure got too high, you could alleviate that. And a simple thing is that you would have a small hole with a valve. When this pressure in the boiler got too high, the valve would open up and release the pressure. And this would be a way to try and control the behavior of the steam engine. The only thing is that this valve would be responding not to what is happening right now, but what happened sometime earlier, because it depended on how much coal was in the boiler. There's always a time delay in any kind of a control mechanism. One was interested in the stability of this control mechanism. Another example is something that we've all experienced if we go to a crummy hotel and take a shower in the morning. So what we do is we turn on the hot water tap and the cold water tap in what we think is the right proportion, and we wait for a while. The shower turns on, the water's freezing cold, and then it gradually warms up. And so you think, okay, everything is fine. You step into the shower, and after a few more seconds, it's boiling hot. And so then you start jiggling with the hot and cold faucets. You turn down the hot, you turn up the cold, and it seems okay for a while, and then it suddenly turns freezing cold. And if you're in a really crummy hotel, you'll be doing this adjusting throughout the entire shower, and it's never right. This feature of responding to events that happened in the past is what makes these sorts of delay systems so interesting, because they turn out to be very rich in their behavior. Let's now be concrete and study a very simple model that has delay in it, and it's known as the Hutchinson model. And so it's basically nothing more than logistic growth, but with a regulatory mechanism that depends on variables at some time in the past. So let's imagine that there's some population n of t, and it evolves in the following way. So n of t dot is equal to r n of t, so that would correspond to exponential growth of the population. But then there is some regulatory mechanism, which I'm not worried about the detailed mechanics of it, but just to write the simplest situation. So I'll write this as n of t minus tau divided by k. So here, if tau is equal to 0, this would just be good old logistic growth, with the carrying capacity of the environment equal to k, and the population would exponentially quickly converge to the carrying capacity k. But we want to ask, what happens now? What is the role of the time delay? This model can be simplified considerably. Let m of t be the deviation of the density from the carrying capacity. M of t is equal to n of t minus k. Let's substitute that into the dynamical equation, and we'll get m of t is equal to minus r m of t plus k times m of t minus tau. Let's now further assume that m of t is small compared to the carrying capacity, and also that the carrying capacity was set equal to 1. Then we get the much simpler equation m of t dot is equal to minus r m of t minus tau. This is the basic equation that we want to focus on.